Let's talk about nuclear energy and conclude this talk on nuclear fission. And uh, if I plot a rough sketch of binding energy per nucleon, this is binding energy per nucleon, and this is mass number. Now, what we say is that the energy obtained from conversion of nuclear mass nuclear mass into energy. We call this thing as nuclear energy, and we can see that the binding energy per nucleon of light nuclei that we have and the heavy nuclei that we have, their binding energies are small compared to the binding energy of the intermediate nucleuses. And and when a heavy nucleus splits into the lighter nuclei, suppose it's a heavy nuclei, it splits into lighter nuclei, then the binding energy per nucleon of the lighter nuclei uh, is uh, is more than that of the binding energy per nucleon of the original heavy nucleus. Thus, a large energy is released in the process of splitting. In the process of splitting, there is a lot of energy that's released. And this process of splitting of a parent nucleus into the daughter nuclei and the production of energy, this kind of phenomenon is known as nuclear fission. And if we take an example of, say, for example, 1 kilogram of uranium on fission, it nearly gives 10 to the power of 14 joules of energy. And if we take a counterpart of it as 1 kilogram of coal, and it gives 10 to the power of 7 joules of energy per kilogram. So we can see that 1 kilogram of uranium is giving an energy 10 to the power of 7 times greater than that of 1 kilogram of coal. So, so on the other hand, when we have the reverse of it, I mean, we have the lighter nuclei, and what happens when the two lighter nuclei fuse together or combine together to form a relatively heavy nucleus, then the binding energy per nucleon increases. So large energy is released in the process, and that process is called as nuclear fusion. Now, let's talk about nuclear fission. And this nuclear fission is basically it's a process of splitting the heavy nucleus into lighter nuclei, and in addition to that, emitting a large amount of energy. So this nuclear fission was basically, it was discovered by Otto Hahn. Otto Hahn and Strassman, the two guys, in 1939. Okay, so what they did is they basically bombarded this. They basically bombarded the uranium 230, uranium 235. They bombarded it with a neutron. So what they did is they bombarded uranium 233 with a thermal neutron, the neutrons that are thermally produced, and they found that the products that were obtained, they were, so if I take it like this, U235 and 92, and and bombarding it with a neutron. So add a neutron here, and and it goes into some unstable state, and then it gives barium and krypton. So barium 141 and 56, and krypton 92 and 36, and 3 neutrons and energy. So this is what is found. They bombarded this uranium-235 with a neutron, and uh, and and the products that were the daughter nuclei that were obtained was barium and krypton, and 3 neutrons and energy. And this Q is basically the amount of energy, which is about it's nearly 200 mega electron volts per nucleus. So, so this much of energy released during this fission, and this energy release is basically the consequence of the mass defect, because there is a difference of mass between the reactants and the products, and that could be that could be expounded like this. So you have uranium, and what happens is you have uranium. It goes to a state of uranium 236, and it's unstable now. And once it's unstable, it gives barium, and it gives krypton, and it gives additional 3 neutrons and energy. So this is it. Now this nuclear fission, it was theoretically explained by Bohr and Wheeler. They tried to explain this nuclear fission process using liquid drop model of nucleus. We will be discussing that in future lectures as we proceed towards the quantum mechanical approach to nuclear physics. So what was, according to Bohr and Wheeler, according to them, a liquid drop model, the nucleus is treated as a drop. It's treated as a droplet of incompressible, uh, electrically charged nuclear liquid. And there are 2 forces in the nucleus that are acting. One is the nuclear force between the nucleons, protons, neutrons, neutrons, neutrons. And so we have nuclear force, and we have electrostatic force. These two forces are there. And what happens is that the nuclear force, because it's an attractive force, it tries to keep the spherical shape of this nucleus. On the other hand, the Coulomb force that we have, due to the positively charged protons, that's repulsive, and the shape of the nucleus remains spherical as long as the nuclear force will balance the Coulomb's force. So if there is a clear balance between the Coulomb force and the nuclear force, then we can have a spherical shape. But when the nucleus is bombarded with a neutron, we have a nucleus, and we have bombarded it with a neutron. What happens? This neutron is captured. It's captured by the nucleus. Okay, it's captured. So we have a neutron. It's captured by the nucleus. This provides some kind of excitation energies to the nucleus. I should say disturbance. It's causing excitation. It's causing disturbance. And this disturbance, this excitation, it favors the repulsive force. Repulsive force, Coulomb repulsive force. If it favors the Coulomb repulsive force, and tends to distort the spherical shape of the nucleus, as a result of this, oscillations are set up within the nucleus, whose shape goes on deforming. It goes on deforming, and ultimately we have a dumbbell shape. And if the excitation energy is large enough, the Coulomb repulsive force pushes the 2 lobes of this dumbbell shaped product that we have into 2 bell parts, and we have 2 parts out of it. Okay, thereby splitting the nucleus into a nuclei of comparable masses. So what we have barium and we have krypton. This is how Bohr and Wheeler try to explain the splitting of the parent nuclei when we have a neutron, a thermal neutron bombarded on uranium atom. Now, however, the reverse is also possible. If the excitation energy is not enough, that the nucleus simply so the neutron is gone inside, but the excitations that have developed inside the nucleus, if this excitation energy is not enough, what simply happens, it emits energy. Uh, the, the, the nucleus emits energy in the form of gamma ray photons equal to the excitation energy. And the surface tension like nuclear force restores back it restores back to the spherical shape of the nucleus. Now, this process is called radiative capture. Radiative capture. All right. So now, the sum of the masses of the product nuclei that we have, the sum of the masses of the product nuclei, it's found to be less than that of the mass of the reactants that we have, neutron and uranium 235. This difference in mass, what we understand is the mass defect. This mass is converted into the energy, which gives us an energy of nearly of the order of 200 mega electron volts. Now, if we take into account this reaction and try to calculate this mass defect, so let me write down this nuclear reaction. So we have a neutron, we have uranium 235 and 92, and what we get is we get barium, and it is 141 and 56, plus we get krypton, and it's 92 and 36, and what we get is 3 neutrons, and we get energy. Now, taking the mass of this uranium 235 and 92 equal to 35.124 atomic mass units, and the mass of neutron that we have, that is 1.009 atomic mass units. Then the total mass of reactants. So the total mass of reactants that will be equal to mass of this and mass of this, and this will be nearly equal to 236.133 atomic mass units. Now let's go with the products. So products, we have mass of barium here, and that's nearly 140.958 atomic mass units. Then we have mass of krypton, and that is 91.926 atomic mass units. And then we have mass of 3 neutrons, that is 3.027 atomic mass units. So we will have the total mass of products. So that will be equal to 235.911 atomic mass units. So we have mass defect delta M. So that will be mass of reactants minus mass of products. So that will be 236.133, and that will be 235.911 atomic mass units. So this mass defect nearly comes out to be 0.222 atomic mass units. Now, this atomic mass unit can be converted into energy by simply multiplying it by 931 mega electron volts. So what we are going to get here is we are going to get the energy released. So energy released in this process. Energy released in this process will be the mass defect. It will be mass defect times 931 mega electron volts. So mass defect is 0.12 triple 2 times 931 mega electron volts, and this energy is nearly equal to 200 mega electron volts. So what we find is that a tremendous amount of energy is released when a nucleus is bombarded, when a uranium-235 nucleus is bombarded with a neutron. And energy released per fission, it simply appears as kinetic energy of the fragments that we have. So they come out with energy, they come up with kinetic energy of fragments and energy of the released neutrons. They also have kinetic energies and energy of the gamma ray photons. That gives us the total energy that comes out in the form of the kinetic energy of these daughter nucleuses and neutrons and additional gamma ray photon energy. And this nuclear fission occurs only if this Q value is positive. It has to be positive when the energy is released. Thus, this nuclear fission it's an exothermic. It's an exothermic nuclear reaction. And nuclear reaction is not possible if this Q is less than 0.